We're delighted to have you join us tonight. And my name is Christine Shupla. I'm one of the many folks who work together to make this available to you. I'm at the Lunar and Planetary Institute, and I work with a number of folks on the MAVEN EPO mission, well, Education and Public Engagement. And tonight's public engagement webinar is being brought to you by MAVEN, one of the Mars missions. And I do see Laura's with us, yay. Laura, would you mind introducing yourself before you introduce Shannon? And I will put my microphone back on mute.
Sure. Hello, everyone. My name is Laura Pedicolis, and I'm a space physicist and education specialist at the University of California Berkeley. And I'm also co-leading the communications plan with Tom and Christine and Karen. So I'm very happy to be here, and very happy to introduce Shannon Curry, who works here at the Space Sciences Lab with me. She is a research scientist involved in both NASA and National Science Foundation research projects at UC Berkeley. Her main focus, as you'll learn tonight, are planetary atmospheres, and especially trying to kind of understand the atmospheres of unmagnetized planets. And she is a member of the MAVEN science team. She got her PhD in 2013 at the University of Michigan, and has been with us at UC Berkeley since then. And just I've known her pretty much since she arrived, and I have to say she is a superstar in the science community, and I'm really excited that you all will get to hear her talk today.
And while we're passing the ball to Shannon, let's hold off on starting your presentation while we're waiting for this little technical difficulty. And Sally wants to know if anyone has any suggestions about her microphone. Anyone have any suggestions on how Sally can, Sally, there's the little microphone icon down at the bottom of the screen. It should be on the bottom left-hand side of the screen. And when you start, it has the little X on it. If you select the up arrow next to it, it might let you select a different microphone. For me, it lets me select a couple different microphones. So select the up arrow, see if you can see if that works for you. And as soon as I get the message that we're ready, we will get started. But I don't want to start the presentation before we're sure that the audio recording is going to work just fine.
So while we're waiting, I can tell a little more about Shannon. Shall I talk a little more about Shannon's work?
Absolutely.
So since we're waiting, I know she was like, that's enough. Just a little bit more about her. She got her degree, her undergraduate degree at Tufts University in astrophysics in 2004. And in 2010 got a master's from the University of Michigan, and then she went to Goddard Space Flight Center. So we have had several presenters on the MAVEN calls from the Goddard Space Flight Center, and I'm sure Shannon knows many of them. So, and just for those of you who may not be in the space biz, it is common for people to get trained in one location and go to another location where a lot of space physics is going on, and then another one. So we end up knowing a lot of one another. We know the community becomes pretty small. That's kind of cool. All right, it looks like we're able to go. All right, so Christine, you want to just take it over again?
Okay, all right. We're going to be passing the ball. I would say literally, but it's not a literal ball. It's a figurative ball to Shannon. Shannon, we're delighted to have you tonight. Please begin and start sharing your presentation for us.
Thank you so much, and a big thank you to Laura, Tom, and Christine for having me. This is quite the honor. So I'm going to share. Let's make sure everything is full screen, and all right. Okay, so is everything full screen and good to go on your end?
Looks good.
Okay, great. Um, so I think a lot of these webinars have focused on MAVEN, and a lot of you have heard a lot about Mars so far. But one of the things that I wanted to talk about today was Mars and Venus as the ground truth or the terrestrial analogues for exoplanets, and trying to think about, why is our focus on Mars so intense, and why do we think about, Venus and Mars as the prime terrestrial planets we go to? So little about me briefly. The reason I got into this was I did an undergrad in astrophysics, but there was something sort of not quite tangible about it. So I got really excited when I went to grad school and started actually working on things you could measure, like even with like an in situ observation. I was really excited by that. And like Laura was saying, I study the atmospheres of weakly magnetized planets. So Earth has a dipole field. That's why a magnet that you may see work. If you had a magnet on Mars and Venus, it would sort of be mayhem. You would just see it spinning around. And so that means they don't have a dipole magnetic field. And I'm really interested by their atmospheres because that has a really different dynamic than here at Earth. I joined the MAVEN team in 2013. And then the Nexus team, which is an exoplanet group that NASA runs, in 2015. And that's my little Bitmoji that you may see pop up throughout. So I didn't know how many kids were tuning into this. So, okay, so the first thing is, why do we focus on the search for water, and why do we focus on Mars and Venus so much? And one of the holy grails in science is life, and trying to find life outside of our planet. And life needs three things. So one of them is nutrients. And this is my main form of nutrition. But really that could be anything, for example, like carbon, hydrogen, oxygen, phosphorus, nitrogen, and sulfur. So that's the first thing that any sort of life form needs. The next things would be energy and then water. And that's life as we know it. Of course, there may be other life forms that are not water or even carbon based. But for now, we're going with what we know. And we know that our sun is the source of energy for effectively everything in the solar system. But water, why liquid water? So one of the things is that liquid water can actually, unlike ice, it can transport nutrients. And unlike a gaseous phase, things can dissolve in it. So liquid water provides a lot of the building blocks for transporting things in for different kind of life forms. So the search for liquid water is the reason we've really started trying to focus some of our science missions. So how do we know there was water in the first place? We certainly know there was water here on Earth. But what you're looking at, I don't know if anybody recognizes these, but on the left, you're seeing Arizona's Grand Canyon. And that's that the Colorado cutting through the canyon. And on the right, you're seeing the Nenadi Vallis. And that's where we think a very similar a river of water was flowing through and creating that sort of geomorphic feature. And that's on Mars. The same thing is labeled here, where you can see a delta on Mars versus a delta in Russia. And these water features on Mars are really exciting. And a lot of you have seen this before, but for us to see such similar features makes it really exciting to know it wasn't just liquid water, that a lot of the same geological features were there. So one of the things we want to try and understand then, which planets other than us and Mars actually have had liquid water? And we think that Venus had water, and we can discuss that later, but that's from the D to H ratio that we see there. We think that Europa, and so you can see, if you can see the mouse here, you can see that Europa was actually one of the things that we started measuring with the HST, perhaps like water geysers coming out. The same thing with Enceladus. We've actually been able to image these fissures in the southern hemisphere where water is actually streaming out. And Ganymede's one of my favorites. It's really cool, and I'll talk about this later again, but there's a very cool experiment they did to try and figure out that there's like an ocean of water underneath the ice. And Cassini just did that observation, so we'll talk about that a little bit later, as well as Ceres. So these are some of the planetary bodies that we think have had liquid water. Now, there could be more. I'm not going through all of them, but these are the ones that I think we've had the most definitive evidence on. It might be worth pointing out that our focus on Mars and Venus is really because when we think about liquid water, it's important to note that that's in the habitable zone. The habitable zone of a planet is basically where a liquid water can actually exist from that distance to the sun, given a certain amount of atmospheric pressure. So Venus is actually right inside the habitable zone, meaning it's just a little too hot, but it's right on the edge. In our solar system, Earth is right in the middle. We're in the Goldilocks zone. And Mars is on the outside. It's still in the habitable zone, but it's pushing the outer limits a little. The thing to note here is that you have to have sufficient atmospheric pressure in order for liquid water to exist. So if we talk about the terrestrial atmospheres of these 3 planets, we're going from cold to hot. So at Mars, the average temperature is like minus 50 C. It's really cold. The atmosphere is really thin and tenuous. And so water would effectively just freeze or evaporate immediately. Like if you threw a cup of water, I think that was seen in The Martian, it would immediately disappear. Earth, we have a nice balmy 15 C. So that's like a reasonable temperature, unless you were in Boulder last week and where it snowed. That's completely unreasonable. And so just if you can disregard that in May, Earth generally is a much happier climate where you can have liquid water and the atmosphere is right around bar. And so that means that we can have water in a liquid form, gaseous, as well as frozen. Then finally we have Venus, and Venus is about 90 times thicker. And so the atmospheric pressure is really, really, really heavy. And because it's so hot, we're talking, I think it's like 400 or 500 C, which is like almost 900 degrees Fahrenheit. Any kind of water would boil off immediately. And that's where you would have to start measuring water within the atmosphere. There would really be no source of subterranean water. But so when we compare these 3 planets, they're really like brothers and sisters, where we know they formed around the same time. So how did they evolve so differently? So the things that affect a planetary atmosphere are going to be, one of the biggest things is the presence of a magnetic field. So at Earth, you can see we have a dipole magnetic field. And again, that's why a compass works. And so when the solar wind goes to interact with the upper atmosphere, what's happening is that magnetic field is actually shielding the planet. And so Earth's atmosphere, a lot of has to do with the fact that we're a certain distance from the sun, but the Earth's atmosphere was shielded by that planetary magnetic field. Now, Venus, comets, and something like Titan, for example, those don't have any kind of magnetic field whatsoever. So their atmospheres directly interact with the solar wind and they start getting stripped off. And that's a little bit like if you open the oven and it's like on broil, it kind of like singes your eyebrows a little. And that's the exact same interaction it has. And so these planets are going to experience a really different kind of atmospheric erosion than, say, Earth would. Mars and the Moon are sort of this like interesting like halvesy hybrid situation where Mars and the Moon have both actually these crustal fields, and crustal magnetic fields are sort of akin to like a magnetic rash. I don't know how else to put it other than it's just these like little dipole fields actually for Mars on the southern hemisphere of the planet, and they rotate with the planet. And so it's like kind of like having like poison ivy on your arm, but you know, it's not a bad thing. That sounds sort of bad, but for us, it's a really exciting hybrid to try and explore the interaction of the solar wind with this really interesting hybrid of magnetic topology. One of the neat things about Mars is that when we see the magnetic field like facing the solar wind, so like right out in front, where we call this subsolar, we find that the escape rate is actually lower. But when it's on the night side and it's not shielding the atmosphere anymore, the escape rate of the atmosphere is actually higher. So it actually serves as a really cool experiment to see that shielding effect. Another thing that affects the planetary atmospheres would be like their interiors and any kind of impact. So for things like for Venus and Earth and Mars, one of the reasons that Venus has such a heavier atmosphere is because it had much more tectonic activity early on in its formation, which means that there was a lot more outgassing. And as a consequence, you then see, and same with Earth. And so Mars, while it has Olympus Mons, it didn't have the amount of outgassing that Venus and Earth did. And as a consequence, it had a little bit less to work with from the beginning. Things like impacts can also really affect a planetary atmosphere. And we don't mean impacts like meteor showers. We mean the way our moon formed. Like there was an impact that was so hard early in Earth's formation, it knocked the moon off. We were originally a much bigger planet. As a consequence, that really does a number on an atmosphere to have a collision on that scale. And what happens is that can either reset the atmosphere, create a secondary atmosphere, or in fact, if it's something like a cometary impact, it can actually deliver water and reset the water at the D to H ratio. So those are all major impacts on a planetary atmosphere. So one thing I wanted to point out is that when we go to try and explore all of these different terrestrial planets, we have to send spacecraft there. And so this is the Mars family portrait of everything really since, let's see, it looks like that was 1960. That was a long time ago. And so you think like, wow, maybe I haven't heard of all of these. That's because most of them have failed. It's really, really hard to get to Mars. And I was actually going to show a curiosity video. If any of you have seen the 9 Minutes of Terror, it's like my favorite video, and I just watch it for fun on loop sometimes. I encourage you to go home and watch it. I'll see if we can try and post a link after this. It's like a 10-minute video, well, a little over 9 minutes. And so, but it's a great video on how they actually got Curiosity to land and just how hard it is. So we actually go through and start thinking about which missions actually succeeded. It's not a whole lot of them. It's actually less than half a success rate. And so here we are, let's see. MAVEN actually made it, which is really exciting. It is alive and well. We're very excited. Launch was really scary for someone like me because I just started my postdoc with Janet Lumen. And I think it was, I don't know, maybe my 50th day of work when we actually went to launch. And most of us were so excited, and we realized when we got there, none of us would have jobs if launch didn't go well. And so there's this like army of postdocs really nervous at launch. And so launch went really well. We had an extra big party because we had jobs. And so that was exciting. But so this is just to give you a scale of how hard it is to actually get to Mars. Or really any other planetary body. And I might point out as well that Mars and Venus, Mars is farther from the sun, right? So it goes Venus, Earth, and then Mars. And that means that there's less radiation. And so that's yet another reason that we like to explore Mars in terms of not only do we definitively know that there was liquid water because of those geological and geomorphic features, but it's actually a little easier to get to. Just the sheer amount of radiation that the spacecraft receives on its way to Venus makes it really tricky. Okay, so here we are with the operational sort of state of affairs with NASA's Mars program. And that's, we are slowly trying to prepare for human exploration. But right now we are here, and MAVEN has launched. We have MRO is still there. We have Curiosity. The Trace Gas Orbiter that ESA launched is fine. They had a rover that didn't quite make it, but again, they're 1 for 2, which is actually slightly above the success rate. 50% is a very strong success rate in terms of sending anything to Mars. So we're still very excited that ESA was able to get there last year. All right, so if we talk a little about MAVEN, MAVEN's primary mission is to explore the erosion of the atmosphere and to try and understand where all the water went. And again, partly because liquid water is such a huge key for understanding life, the solar system, and really just the evolution of all of these planetary atmospheres. Some of you have probably seen this ad nauseum, but so I'll quickly go through it. But so we have Mars. These are the different escape rates, or excuse me, the escape processes. The sun is the main driver of atmospheric erosion. And things like CMEs, which are coronal mass ejections, or SIRs, which are stream interaction regions, these are all solar transient events that can start to just, they sort of act like if there's a flood, if there's just normal erosion, say a dry riverbed somewhere, it's just slowly eroding with wind. And then all of a sudden this flood comes by and washes the thing out. And that's what solar storms do to planetary atmospheres. We also have things like genes escape. We have pickup ion escape, photochemical and sputtering. And we'll talk a little about that in a minute. So one of the first things, the first thing we'll talk about is the hydrogen escaping. And the genes escape is basically just when a neutral has enough escape velocity or escape energy to escape gravity from the planet, and it can just fly away. Typically hydrogen, because it's a lighter element, it's sort of just like a lighter balloon. It sits farther from the planet, and it's way above it. Its scale height is much higher than that of oxygen or CO2. And so it tends to escape pretty easily via genes escape. One of the interesting results that MAVEN has seen, and here you can see, this is one of the really cool actual images that IUVS took on our cruise flight in. When we went to our 40-hour capture orbit, our orbit now is about 4 hours, but the capture orbit was about 40. And that means that we could really stand really far back and get the full view of Mars and this hydrogen corona and some of this hydrogen escape, which is really exciting because you don't get that many opportunities. All of a sudden, you're really up close. And so this was an exciting opportunity to do that. And we found that the hydrogen escape is really limited by some of the chemistry, and that we think that actually a lot of the hydrogen escape that we're seeing now is seasonal. And we never thought that before. And part of that is because we think that there's a source of water in the lower atmosphere, whether that's an evaporative process or it's just something, a residual aspect from some of the water evaporation from billions of years ago. There's a source of water in the atmosphere that's creating a really variable amount of the hydrogen escape. And we're going to be focusing on hydrogen and oxygen escape because water is H2O. And so those are the two big things we like to look for. There are other elements escaping, but just so you know, we'll be focusing on those two constituents. Oxygen escape at Mars. So photochemical escape really just means that there was a collision and something was given enough escape energy to actually, again, to get away from Mars. And so photochemical often refers to something called dissociative recombination. And that's usually just when O2 plus recombines with an electron to create two O atoms. Anybody out there? An ion is just something that is missing an electron. So like O2 is the same as O, except that it's just missing one electron. So when it recombines with that electron, these two oxygen atoms are formed. And what they do is when they like recombines, they actually branch off like that. And so they go spinning, and usually one goes up and one goes down, and one goes down, rejoins the atmosphere, and one that goes up has a chance of getting away. There are ways to calculate the probability of that. But the short of it is that we've seen really high escape rates earliest in the mission when we had a higher EUV irradiance. That's because of the solar cycle, and I forgot that slide, but maybe I can try and post it. The solar cycle is incredibly quiet right now, sort of disturbingly so. We as scientists like to see natural disasters and cool things, especially at other planets. And we've seen a really quiet sun, so we haven't seen that many storms. We haven't seen really like interesting epochs of high EUV or densities. So that's just one thing that early on in the mission, we were lucky to observe some of the most exciting things from the sun because we're in the declining phase of solar cycle 24. Basically, the sun's in its 11-year cycle and does this. And so when you're at the top of the cycle, that's when all the fun stuff happens. And we're kind of on the way down right now. Cool things are still happening, but to try and observe some of this escape when we saw the highest EV was really exciting. So here, seasonal longitude is how they measure the season. And so it's happening as MAVEN is going around in a highly elliptical orbit. What it's doing is as it gets farther from the sun versus closer to the sun, that's when you actually you're in a different season, sort of much like you're at Earth. And so what's happening is that some of that EUV early on, we actually got to see at a really high rate. And you can see that this escape was highest during that high EUV phase. We also have oxygen escaping via pickup ions. And this is a plot by Yashwei Dong at Boulder. And these are the ions. So again, it's just oxygen minus an electron. And the cool thing about ions is they observe electric and magnetic fields. And so unlike neutrals, the solar wind, so this interplanetary magnetic field that the solar wind drags off with it, it reacts to all of that. And here you can see that all of these ions are starting to sense the magnetic field as it wraps around the planet and actually start going spiraling off with it. Yashwei discovered something really exciting called this polar plume. And that you actually don't really see at that many other planets. It's because Mars is small, and because it does not have a magnetic field, it can actually, all of these, it's almost like a mohawk in terms of the actual escape. And so you see escape coming like almost like right off its forehead, following all the way back into the tail there. And that's something that's never actually been observed, because MAVEN has both a magnetometer as well as as plasma instruments. And we haven't had both at Mars since Phobos, and Phobos was like over 25 years ago. So the other interesting thing about the plasma environment at Mars is that it can actually create precipitation. So some of those ions are getting swept away by the solar wind, but some of them are actually crashing back into the planet. So I'm trying to grab my mouse. You can see these arrows. These arrows are the direction of the plasma. So here the O plus is flying away from the planet, but here you're seeing it and it's crashing all into the southern hemisphere here. When that happens, you can get something called sputtering. And sputtering is particularly important because we actually think it's the main process that stripped Mars of most of its atmosphere. So what is sputtering? So sputtering is basically when these heavy, heavy ions come crashing in and splash neutrals off. And it's a sort of akin to doing a cannonball in the pool. If you lightly step in the pool, not a lot of water is going to come out. But if you get a running start with all of your friends and you jump in, that's what happens when heavy ions hit the atmosphere down here and all the water comes out. And at this point, it's sort of like figurative and literal because it is splashing oxygen out. But that's how those neutrals can escape the system. What's interesting about sputtering is that Bruce Joukowsky, our PI, and one of his grad students, Merrick, have done a lot of studies on isotopes. And we know that sputtering was important because argon was was one of the main constituents, or a major constituent of Mars's early atmosphere. Argon is inert and it's a noble gas. And so that means that it cannot chemically react the way the photochemical escape can, like this. So argon can only be stripped away by something like sputtering because it does not react with anything else. And when you look at the argon isotope ratios in Mars's current atmosphere, we can tell that between 30 and 60% had to have been stripped out already. And there's only one way to do that. And effectively, we think that that's sputtering. So that's given us, while sputtering is not one of the main drivers today, it is a really exciting escape process to study because it may have been the major, major source of atmospheric erosion early on. Venus. So Venus actually undergoes all of the same things. So I won't repeat myself and show you, they're really similar plots because they're pretty similar planets in many ways. There's CO2 atmospheres, they're weakly magnetized. This is a plot from Ricard Lundin, and this was using VEX. And one thing to note, VEX had a magnetometer and a whole plasma suite, so it could measure things that like MAVEN does. For some reason, maybe because Venus didn't have a magnetic field, when VEX is the Venus Express, they went to go build an identical spacecraft effectively for Mars called Mars Express, but they just didn't put a magnetometer on it. And so that was sort of on the bottom in terms of like the funding cut. And so it never went with the magnetometer. So VEX and MEX actually didn't quite measure the same things at the respective planets. And that's why when MAVEN finally came, we got to measure all those neat things. At any rate, so what you're seeing with Venus here, you're seeing the O plus, and this is the H plus. And here you can see that energization. And so this is the energy, and this is a log of the energy. And really this is just showing you is that as VEX actually went through the atmosphere during periapsis and came back out, it was sweeping through, measured a lot of these heavy ions here. Here, this is the solar wind. It goes through the induced magnetospheric boundary. And then it starts to observe all of those heavy oxygen ions getting accelerated. So this is the same stuff that MAVEN actually got to see, but at Venus. So a lot of the same things. One thing to note is that the temperature and the radiation at Venus have always been more extreme, simply just because it's closer to the sun. And so it will always be getting more radiation than Mars will. And the temperature we'll talk a little bit about.
Hey, Shannon, before you go on to that, there's a question about why is the escape rate over crustal magnetic fields lower on the day side and higher on the night side?
Sure. Think about it like an umbrella. I mean, it's very similar to an umbrella. If there's like sheeting rain coming at you, actually, and like this is sort of like a good image to show it. If there's sheeting rain coming at you, you're gonna put the umbrella in front of you to try and like block your head or your face, not in back of you. You know, when it like pops out in back of you, you're just like, Awesome. And so that's what happens effectively. So when the crustal field is in front, it's quite literally shielding some of that atmosphere, because as the solar wind comes in, the stagnation point is farther out. And so it actually has to flow around the stagnation point farther out, as opposed to when it's on the backside, it can come all, like, it's just raining on Mars's little face there. So to me, it's a lot the way I would think of like an umbrella is. Does that help? I'll go on. If there are any other questions on that, I can talk more about it. I may have some backup slides to sort of show some examples. But I think that that's probably the easiest way to look at it. And actually, you can sort of see it here in these background fields. The top row here would be the magnetic contours. So this is the strength of the interplanetary magnetic field. These white lines, that's the sun's magnetic field draping around both Mars and Venus. And on this bottom row, this is the flow of the solar wind. And so the solar wind and then the electric fields are just superimposed on top of it. So you can see here the solar wind's really fast. It's coming at these planets. You know, this is Mars, this is Venus. So here, all of a sudden the stagnation point here and here, this is where Mars's magnetic field starts to pop out and actually stands off farther away. So when that flow comes, it has to come farther out. So it actually can't interact quite as much with that upper atmosphere. It still does, because this is not a full dipole field. So it's much, much different than Earth. But you can see that because of these little crustal fields, you actually see more asymmetry in the magnetic field contours. Like at Venus, things are relatively symmetric around here. But Mars, you start to see a lot more contour depending on where that crustal field is. And the same with the bulk flow. And this creates a really different kind of it creates a really different magnetic topology, which really influences, especially the way the plasma escapes. Like, for example, down here, all of these arrows are the electric fields, and you can see they're pointing almost away from the planet and down, and that's that polar plume. Whereas Venus, it's much smaller, and you only see a few of them starting to point. And that's just an example of the way the solar wind interacts with Mars and Venus differently. You also might notice it's just simply stronger. This is a color contour. See how it's lighter green here and darker blue here? That's because the strength of the magnetic field and the velocity of the solar wind are just hitting Venus faster. So they're driving up that escape rate. So what does that actually mean in terms of the historical loss rate for Mars and Venus? So Mars, we've done all these really cool calculations. We've gotten together a few times. We just had this really great aeronomy conference in Boulder last week, and we got to take a look at adding all of these escape rates up. So that's your photochemical, that's your sputtering, that's your ion loss, integrating it over time. And so you can hear those isotopes constraining what that is. You add in some solar storms, and you try and think of what those escape rates are, and you integrate it. And we think that if you integrate over about 3.5 billion years, to where this liquid water point was, it would have been the equivalent of over 15 meters of water or a bar of atmosphere, which is consistent with some of the findings that some of the geological evidence that Mars has provided. Venus is sort of a wild card. It's really unclear what happened in general. It's so hot there, it's really hot. And so on the one hand, you might say there's no way life could have existed. Maybe there was water the first billion years, but then it must have really quickly evaporated, which then meant that you're stripping a lot of the oxygen and hydrogen out of the atmosphere. So then that CO2 starts to collect, and that's where that runaway greenhouse effect comes. But early on, there's actually a thought that if there was water there, it would have formed clouds, because it was so hot that you would have a constant, like a cloud process. Sort of the way, like if you're in Florida in the summer, there's at some point it always storms, and it's a similar idea. And if that was the case, the clouds would have actually shielded the surface from some of that temperature. And Michael Way in 2016 got together with a bunch of the other NASA GCM, the global climate modelers, and they actually found a scenario where it was only maybe 20 degrees hotter than Earth about 3.5 billion years ago or 3 billion years ago at Venus. And it could have had water. So that's been a very recent and exciting development in terms of possibly harboring life. Okay, so one of the things is here we are talking about the habitable zone in terms of, okay, Mars, Venus, Earth, but our habitable zone will change because our star is going to change. So this is our current sun in the top panel, and it's about 4.5 billion years old. And you can see here in the habitable zone, this is where Earth is, and that's where Mars is. But in another 8 billion years, the sun's going to become a red giant. It's aging, like all of us. And so our particular sun will expand. And what's going to happen is that it will actually swallow the first couple planets. And additionally, it'll push our habitable zone way out to Jupiter and Saturn. And this is the part where we get to come back to those some of those gas giants and some of their moons. And one of the things that I just wanted to talk about here quickly, especially with really extreme Earth, really extreme life forms, we've found life in odd places on Earth where basically we have no business seeing life. Like you see them in these sea vents where there's zero sunlight, and I mean zero sunlight. We've seen them in the Yellowstone hot springs where, let me see that I wrote this down, the pH has a value of 1. That can dissolve a nail for anybody that doesn't have their pH scale right on them. That's really, really strong. And we've actually found life there. Same thing with the Antarctic, the subglacial lakes. I mean, they've been under there for hundreds of years. I mean, they're like incredibly cold. There's very little light, and we're still finding life forms. Same with the Atacama Desert. The Atacama Desert, so there's something called the relative humidity. That's how you measure just moisture in soil. It is so dry that the MSL rover at Mars, it measured the same relative humidity in the Gale crater as it did in the Atacama Desert, just as a point. When we say Mars is really dry, so is this desert, and we have still found life there. So it's just worth considering. So one of the cool...
Can I ask you to pause for just a second? We've got another question.
Please.
The question, kind of maybe back 2 slides, with the Venus magnetic field being so weak and given its proximity to the sun, how is Venus maintaining its present dense atmosphere, and when do we expect it to lose its atmosphere and end up like Mars?
That's such a good question. So it may never end up quite like Mars. I mean, again, all 3 of these planets have evolved really differently. Venus is able to keep its atmosphere because of the greenhouse effect. And so we see that to some degree here at Earth. I won't focus too much on that because that starts to get into Earth climate, which is its own many, many, many hours of discussion. But at Venus, that greenhouse effect is able to then basically replenish the atmosphere. And especially because it's already so thick, it's sort of a snowball effect. Poor choice of word, but it's the expression meaning everything sits lower in the atmosphere. So Venus is about the same size as Earth, where Mars is 1/10 of the size. And so Mars just has less gravity. Gravity here is around 9.8 meters per second. For there, I think it's like 3.7 meters per second, so 1/3. And Venus, if it's got our gravity, it's keeping that atmosphere closer. And because the atmosphere is much heavier and it has these heavy things, the scale heights are all lower. So it's physically binding that more. And then plus the circulation patterns with that greenhouse effect, that's actually what's keeping it. In addition to early on, it had much more outgassing. So it had much more atmosphere to work with, probably than both Earth actually and Mars, but definitely Mars. So that's one of the big reasons that Venus and Mars are currently different. It will eventually be stripped, particularly if you look in this habitable zone, especially as our sun starts to expand. It's eventually just going to start getting burned off very quickly. But that probably wouldn't be for another couple of billion years. And that's one of the climate modeling things. Most of us look back in time, not forward in time. So I'm not sure how long it would take to burn off, but 2 billion seems like a good number. But I can double check and get back to whoever asked the question with like an actual citation on that. So, okay, I'll pick, there we are. Anyway, so for some of the moons we're seeing, this is Europa, this is an HST image, and you can start to actually see some of the water vapor plumes erupting from that southern hemisphere, which is really cool. And again, especially, I say when the sun expands, we'll all be long gone, but this could be a very different scenario when that happens. Same thing with Enceladus. We've actually, again, imaged this. And so with Enceladus, the same thing. We've actually started to use Cassini and able to see these plumes coming out from, they're called these like tiger stripes on the planet. And it's these giant ice fissures where we actually think that there's liquid water beneath, because nothing else would eject these kind of jets the same way. Okay, so Ganymede, cool story. So Ganymede, basically, HST was imaging Jupiter and Ganymede at the same time. And they started looking at the aurora really carefully. And so when they were watching the aurora shift as Jupiter's magnetic field moved, and what they did was they figured out that in order for an aurora to shift like that, it couldn't have just been on a solid planet. There had to be a saltwater ocean underneath in order to make the aurora move like that, given Jupiter's magnetic field. And the subterranean ocean at Ganymede, no joke, is actually, scientists think that it's more water than all of Earth's surface. And so this is a lot of water. I think that's the coolest thing ever, just to see from an aurora, and for there not to be another plausible mathematical explanation. So that's Ganymede. And I skip series. Titan, I just feel like it needs a shout out because it doesn't have water, but it has lakes of liquid hydrocarbons. And we sent the Huygens probe down to its surface, which a lot of people don't know. But we sent a lander all the way to the surface, and it took pictures and it took measurements for about 90 minutes there. And that's still the farthest we've ever gone and landed on something, which I think is just great. And so anyway, it landed actually probably in actual liquid before turning off. And so you can actually start to see like glint and reflection. And so we were actually able to see the fact that there was liquid on these like methane lakes all over Titan, which is just pretty cool. Okay, that brings us to exoplanets. And so here we are thinking about Mars and Venus. They're really different, but they've both had liquid water. There are different studies suggesting both could have been habitable. Venus is a little outside that zone. But again, if you take a really flexible habitable zone, maybe it's almost in it. So what can we learn? Here are Venus, Earth, and Mars. Again, you can see it's like right on the outside. This green is a conservative estimate, and the darker green is sort of on the outside. Both Earth and Mars are in the habitable zone, and this would be our star and the temperature of the star. And this is sort of the energy received by the planet. So it's scaled to Earth, which is 1. Mars is farther out because, as we know, these are all the small, like super Earth or Earth-sized planets that Kepler has observed. 10 years ago, we could only see hot Jupiters that were like right next to the star. This is an amazing, all of these were found in the last like 5 years, not even like 3 years. It is amazing how far we've come and how fast exoplanet science is accelerating. And so the size are actual relative to Earth. And so we call most of these super Earths, but you can see, I think it's 1229b. We finally started observing the first Mars-sized exoplanets. I say observing, and it's really we're sensing their transit. But that's incredible because it's really hard to do. And here's an example of why. When a planet transits, what's happening is that it's going in front of the star and blocking some of that sunlight. So there's a dip in its light curve. And that means that there's a primary eclipse and a secondary eclipse as it goes around. This is important because this is how we start to sense the atmospheres of exoplanets. So we talk about transmission spectrum and emission spectrum. Transmission spectrum is when it's transiting right in front, is the atmosphere crosses that star, and we can actually see through, almost like a limb sounding that we do on MAVEN with IEVS. We can start to see different absorption features and spectral features of the atmosphere of that planet. Emission spectrum is different. Emission spectrum tells us about the actual planet itself, because what you're doing is you're measuring, while the planet is actually right out here, what you're measuring is the star plus the planet. And then when it goes behind the planet, you can measure just the star. You take the difference, and that's the emission spectrum from the planet. And using those two things, you can look at different, you can take the depth of that light curve and understand things like the distance from the star, the orbit, the size, and then possibly the mass. This is what the absorption or the transmission spectrum might look like for Earth, Venus, and Mars if you were 10 parsecs away. So like some of the close stars that we actually see. And so if you were at something like, well, maybe not Aquarius, but if you were at a near stellar neighbor, this is the kind of spectra you might see if you had no observational problems whatsoever. So from like their next JWST. This tells us, especially for Venus and Mars, even though they have CO2 atmospheres, those features are really different. And that's because, especially with Mars having such a thin atmosphere, it doesn't absorb as much, and you don't get that transmission the same way you would with a much thicker atmosphere. These are the first 5 light curves that Kepler ever discovered. Now, these are different stars and different planets, and it kind of just shows you quickly, like, for example, this is a star where the planet was really, really small compared to the disk size of the star. And so the light curve was really, really small. Kepler 5b, however, the planet was much bigger compared to the disk size. And the amount of time it took to transit, you saw a deeper, wider light curve. So all these light curve shapes tell you something different about the orbital period and the size of the star. And that's how we start to characterize them. When I'm showing you all those super Earths, that's how we start to do that. The first transmission spectrum that we saw from an exoplanet was by Dave Charbonneau, and he's at Harvard. And he found this sodium doublet. So we're at 590 nanometers. This is visible light. If you're not immediately familiar with that wavelength, that's bright yellow in the visible spectrum, and that happens to just be the sodium doublet line. And so that was a very cool thing to see from an exoplanet, is that it would actually have the color yellow in its atmosphere. The TRAPPIST system, I'm skipping all the really cool observations of exoplanetary atmospheres between now and then for the sake of time, but the TRAPPIST system was the latest big NASA press release, and this is the whole TRAPPIST system, and it's orbiting an ultra cool dwarf star. It's actually only the size it's only a little bigger than Jupiter, their star is. We found all of these interesting planets, and it's in the Aquarius system, and it's about, let's see, I think it's 12 parsecs away, which is about 40 light years. That's actually not that far. That's pretty close, and so very exciting discovery. And this is actually the first transmission spectrum from the TRAPPIST 1b and 1c. By the way, those naming schemes, really boring, but A is always the star, B is the first planet, C is the second planet, D, et cetera, et cetera. And so it's actually, so B and C are these 2 planets here. All of these are super Earth-sized. We think that they're terrestrial. Just to quickly point out here, they tried to figure out what was in the atmosphere, and given the light curve that they saw in that transmission spectrum, and it's tricky. It doesn't quite match any of the models. And that just goes to show you that we have a lot of work to do to try and figure out what goes into atmospheres and how different they are. We feel like we're starting to just get a handle on why Mars and Venus are so different, as to the earlier question. These exoplanets are really tricky, and it's really hard to model out the atmospheres, but it's exciting that we can even see these measurements, because it's these incredible worlds that I don't even think we've fathomed yet, and here we are observing them. Okay, JWST is one of the next missions to help us observe these exoplanets, but it'll do great things for the solar system observations as well. This is an infrared instrument, so it'll really help looking at some of those atmospheres and absorption line spectrum. TESS is the Transiting Exoplanet Survey satellite. It can stare at really, really bright stars and for a much longer time and help us identify a lot of the things that we couldn't originally do. Both of these are incredibly cool instruments. I might point out just another fact. I'm supposed to be pitching JWST a little more. JWST both launched actually in 2018. This actually has it's like the size of a tennis court, the star shield here. Basically, like on the top, I think it's hotter than Death Valley, and on the bottom, it's colder than Antarctica. And that way, it cools itself really carefully and take these really beautiful measurements. We're all supposed to say it can resolve a penny from 24 miles away. So we're very excited to see what it can do with an exoplanetary atmosphere. Okay, pale blue dot, just to end on a happy note. Hasn't been the best few days in the news. So I will leave you with this. Thank you. It's my favorite Carl Sagan quotes. I'll let you guys read it. Are there any questions? Christine, I don't think I can hear you.
Sorry, I was on mute. So those of you who have questions, please do enter them now in the chat box, or if you would like to unmute yourself to state your question, that would be great. So while we're waiting for people to finish thinking of their questions, because I'm sure there are quite a few, of the planets that have been discovered, just based on the little bit that we know about Mars and Venus, would you have any expectations as to which ones might have started to be stripped based on their positions or their mass, expectations about what their magnetic field might have done?
Magnetic fields are really hard to sense in exoplanets. I think maybe it's something like a hot Jupiter, like the huge gas giants with really big magnetic fields we can start to. But in terms of atmospheric erosion, those transmission spectra will start to tell us a lot about that. Actually, the TRAPPIST system, while it's such a cool discovery, the X-ray and EUV flux there is really, really strong. And so most of us who have started doing preliminary modeling of the TRAPPIST atmospheres, no matter what the composition is, in truth, those atmospheric lifetimes will be short because they're close to their stellar host, and that kind of radiation, you have huge ionization frequencies, and they're not going to be able to last. You'll be ionizing things, they'll be colliding in between those collisions, and just then simply like that much energy in the atmosphere, it'll be stripped pretty quickly. Compared to something like having Earth as a stellar host. And so those planets will not have long atmospheric lifetimes, not the way like Venus would.
So would you suspect then that the TRAPPIST system planets are less likely to be inhabitable based on that?
No, well, it's sort of an interesting, I mean, statistically, yes, but when you look at how long life has been around compared to the solar system, we're a pretty small sliver. I think sometimes, you know, they like in a minute you can play the history of like the universe or the solar system or something, and we're like last like, oh, I think it's in a whole day. If the universe was in a day, we'd be like the last 9 seconds life would enter then. So it's possible that maybe even if it's for only a couple 100 million years, I mean, we think of the dinosaurs as so long ago, but really considering it wasn't, I mean, we're talking about 4 billion years for just our solar system. And so I think that life only takes, I mean, you need a handful of healthy years, which for life, call that, you know, 20 to 50 million. That's still a fraction of the age of a stellar system. So maybe, statistically no, but maybe, considering, you know, astrobiology has really taken off and we have seen really extreme life forms here on Earth.
It looks like we've got a question. Are there any NASA Mars or Venus orbiters planned for the future? And what type would you like to see next for Venus or Mars in terms of orbiters?
So in terms of Mars has a couple. I'm just going to go back really fast. I think ESA has a couple, and we certainly do. Let me see. I'm looking because sometimes there's certain things that are in proposal phase and you're not supposed to talk about them. Okay, so things like we have like ExoMars coming up, and there are a couple of different rovers. We already had a few launches. So I think the ExoMars 2020 will be exciting. In terms of orbiters, EMM, the United Arab Emirates, is actually launching an orbiter, and I think that's going to be in 2022. Maybe 20. No, it couldn't be 2020. Let's say 2022. Actually, I don't think it's here. The MOM mission, India launched that. Oh, there it is, the Mars orbiter. So right now, those are the ones slated for Mars. Right now, almost everything we have coming up will be a rover. I like the rovers, but I'm definitely, in terms of like the water on Mars, there's sort of, water can go up or down, and I'm on team up. So I'm looking for a few more of the satellites to get there. I would love to see more plasma instruments, especially. Like I'd love to see a solar wind monitor at Mars, because understanding the solar wind within the heliosphere, so what the solar wind looks like at Earth, what it looks like at Mars, what it looks like at Venus, is really, really important to try and understand space weather effects, just as well as the way it erodes planets, given their distance from the sun. And again, that also has a really big effect on how all of these atmospheric lifetimes, especially when we think about exoplanets. So I would love to see solar wind monitors at every terrestrial planet, but NASA's budget is only so much.
Are you aware of any Venus orbiters coming up?
Oh, they're sort of, I think they're musings about doing some small sat work. I think increasingly looking at the budget that we have, small sats and CubeSats are looking more attractive to NASA. And that's something here at the lab we're trying to get much more involved with. Those are really important aspects for, just because they're cheap, and a lot of them you can just fly legacy instruments, so instruments that have already been proven to work in space, and you can use the same ones. So it's sort of like an off-the-shelf kind of mission. And so I think that would probably be the direction with Venus.
Folks, we've got just a couple minutes left. Anyone have any additional questions?
I can't see any of them, so I'm hoping you guys just read them to me.
So far right now, people enjoyed the presentation.
Okay, good.
Kay, can you hear any questions on the phone line, on the NASA line? Were there any questions that we haven't heard from NASA folks, maybe?
I can also leave my email, by the way, if anybody, not everybody, if anybody does have a question afterwards, or is not publicly inclined to ask anything, I think I can add my email to the slides if anybody wants to download them. So feel free to email me if anybody thinks of anything after the fact.
We have one last question here. Given the stripping of the Martian atmosphere, do you believe the plans to land people on Mars and the SpaceX plans to have people habitate Mars is worthwhile?
I do. The rate of atmospheric erosion is not enough that it will change significantly the atmospheric pressure in the next, say, 15 to 20 years. The atmospheric pressure is already, it's really light there. And so as a consequence, we're still going to have to figure out, we're going to need shielding and suits and all of that, because right now, if you were there, your blood would boil or freeze without a pressurized suit. So that's still going to be that no matter what. So I think it's still worth going. I think people on Mars probably, there are a lot of big questions on whether you should do that. Atmospheric pressure is probably not the biggest concern, but there are obviously plenty of others. So that's a big debate. But I think in terms of the pressure and the stripping, in the next 50 years, it'll be fine. Another million, it's going to be miserable.
Shannon, are you okay? I have your berkeley.edu email if I put that in the chat.
Absolutely, yeah. Please feel free to send that out. And if anybody has questions, feel free to email me.
Thank you.
Well, that's about the top of the hour. Thank you, everyone, for joining us. And thank you, Dr. Curry. We really appreciate your time this evening. And we really appreciate it. Everyone, we look forward to seeing you again at a future webinar.
Have a great evening. Thanks so much.
Thank you so much.